Hello students, today I am going to start new unit of your syllabus, that is active filters and oscillators. So first I will start with your unit, that is active filters. So what basically a filter is? So all of you are aware the word filter. Filter is removal of unwanted things from the desired things. So it can be defined as a mechanism or a device used to eliminate undesired things, maybe particles, maybe unwanted electrical signal. There are plenty of examples around us. Water filter, in which you purify your water from contaminations and unwanted minerals. Air filter, this is being recently used by all of us. Then fuel filter in vehicles to purify the fuel which is being used in the engine. Then recently we are using N95 mask. So this is also filter. So it filters unwanted organisms to enter our respiratory system. So stay safe during these times. Corona, COVID-19 disease, using N95 masks or any masks of suitable things designed at your home. So noise filter is a prominent thing as far as electronics is being concerned. Your mics, your audio system, your videos, everywhere noise is present, and it becomes a very difficult scenario if we are not able to eliminate them. So that's why the role of filters are very, very important for electronics engineer. So I try to get you people understand the basics of filters. So filters in electronics. A filter in electronics can be defined as a frequency selective circuit that passes a specified band of frequencies and blocks or attenuated signals of frequencies outside this band. Filters may be classified in several ways. Few of them are analog filters or digital filters, passive filters or active filters. So analog or digital signals depends upon the type of filters they are going to filter. If you are filtering analog signals, they fall in the category analog filters. If you are filtering digital signals, they fall in the category digital filters. Passive. If you are using only components like resistance, inductance and capacitors, they fall in the category passive. And if you are using BJTs, diodes and MOSFETs, then it falls under the category active filters. Filters can also be classified as the range of frequency for which we are employing the filter. So it can be audio filter or it can be radio frequency filter. Depending upon the band, the filters can further be classified as narrowband or broadband filters. Other classifications are there. IIR filters, FIR filters, which you are going to study in the course of digital signal processing. So right now, the main focus of this particular presentation or lecture is to give you the fair idea of how filters behave. So we are working on passive filters, and later on I will tell you how passive filters can be used in conjunction with your active filter components to make active filters. So now, what are the advantages of active filters? In the conventional things, we don't have this flexibility. So when you are going for active filters using operational amplifier or some BJT amplifier or MOSFET amplifier, then it gives us some freedom. It gives us freedom to adjust gain and frequency. There is no loading problem. If you are using conventional RC filters or LC filters or RLC filters, some sort of loading problem is always there. because all of you are aware that impedance matching is not there. So to match that thing, loading problem is always there. So in this particular case of active filters, there is no loading problem. Another important aspect, as far as these days we look forward for low cost, so it is one of the reasons, and we call it advantage of active filters. So most commonly used filters are low pass filter, your high pass filter, your band pass filter, your band reject filter, and all pass filter. Now in the presentation to follow, I will be discussing each of the filters in simplest manner, so to get you the very good idea about how filter works. So first is low pass filter. So before I start with low pass filter, I would like to revise this particular formula. This is called capacitive reactance. So it is the reciprocal of 1 by 2 pi Fc, where F is frequency of operation and C is the capacitance used in the network. So from this formula, we are aware that at low frequencies for DCs, Xc is almost infinity. So your capacitor offers very high impedance at low frequencies, so it does not allow anything at low frequencies to pass through it. So this is what we are going to use in this particular filter definitions. So this is a diagram of low pass filter. So here you have, this is basically active filter, passive filter. This is a resistance, this is capacitance. You are applying input from here. You are applying a particular frequency input from here. So now when your frequency is low, what happens? This is offering a very high impedance. So your signal directly is available at the output. Slowly and slowly what happens? Your impedance start decreasing, capacitive reactance start decreasing because frequency starts increasing, this capacitive reactance starts decreasing. So some of the things will be grounded, and at very high frequencies, instead of going here, your output is 0. So this is your ideal frequency response. That means at low frequencies, everything is passed, and at high frequencies, it does not allow anything to pass through it. So in this figures, you find out two terms, pass band and stop band. So the frequencies below higher cutoff frequencies which are being passed through your filter falls under the category pass band. So the band in which the frequency is being passed is called pass band, and the band in which your frequency is being stopped or attenuated sufficiently so that it does not pass through this is called stop band. So filter is nothing but just the adjustment of these two bands, pass band and stop band. If you change the bands or swap the bands, what happens? It becomes high pass filter. So this is the ideal frequency response, which does not exist. Practically, your practical frequency response goes like this. So here you will find out FOH, higher cutoff frequency, and here you have minus 20 dB per decade slope. Now some of you may ask why this slope is there, minus 20 dB per decade. So here we have only one capacitor, and if you find out the transfer function of this as we have done in the previous lectures, you will find out that only one pole is there. So one pole is there, so that leads to the slope of minus 20 dB per decade. If more capacitors are there, more poles will be there, then the slope becomes minus 40 dB per decade. So it also accounts for one thing that is called order of the filter. We will discuss that later on. But to let you people the idea here, this is first order filter minus 20 dB per decade, second order minus 40 dB per decade, third order minus 60 dB per decade, and so on. So to get your ideal frequency response closer to practical frequency response, we are supposed to increase the order of the filter. So that we will be discussing in the next class. So now next is your high pass filter. So this is your high pass filter. Here your capacitances and resistances are interchanged. So at low frequencies, this capacitor will block everything. So your signal is heavily attenuated. So this is your stop band. This is your stop band. This is called lower cutoff frequency. And at high frequencies, it allows everything to pass through it. So this is your high pass frequency. So here you can notice that your bands are actually swept. So this is your stop band and this is your pass band. Again, this is your ideal frequency response and this is your practical frequency response. Again, this slope is there of minus 20 dB per decade. So I hope you get the fair idea of low pass filter and high pass filter. So now I move ahead. Now combining low pass filter and high pass filter gives us a very wonderful results. Using these two, we can have your band pass filter or band reject filter. So you have a signal input. It is being passed simultaneously through low pass filter and high pass filter. So whatever is common will be eliminated and whatever which is not common will be available at the output. So this is the basic fundamental of band pass and band stop filter. So this is your band pass filter. So band pass filter is basically combination of high pass filter and low pass filter. So when high pass filter and low pass filter are being combined together, then we have intersection of lower cutoff frequency and higher cutoff frequency. So suppose this is your low pass filter response and this is your high pass filter response. So the area which is common, sorry, this is low pass filter, this is high pass filter. So the area which is common like this is actually the response for band stop filter. So this is the practical response. This is your lower cutoff frequency. This is your higher cutoff frequency. So lower cutoff frequency is being denoted by F, O, L and higher cutoff frequency is being denoted by F, O, H. So this is intersection of these two, lower cutoff frequency and higher cutoff frequency. So this is your band pass filter. So using this particular mechanism, what we are actually achieving? We are achieving that the particular band of frequencies is allowed to pass through your filter. So next is your band stop filter. So how you have actually created band stop filter? You have input and it is being passed through low pass filter. It is being passed through high pass filter. So your low pass frequency response is like this. Your high is like this, and you're actually stopping a band of frequencies. So this is pass band, this is pass band, and again this is your stop band. So both of them are intersecting each other. So common thing is being allowed to is rejected, and which is not common is allowed to pass through that. So sometimes it is the requirement that particular band of frequencies is stopped and other two pass through. Maybe a spike in there in your voltage, so that particular spike is eliminated. The rest of the signal is allowed to pass as it is. So I hope you get the fair idea of four kind of filters: low pass, high pass, band pass and band stop filter. So next kind of filter, this is a band stop filter using your active components and passive components in conjunction. So this is your high pass filter, this is a low pass filter, and both of the responses are being combined to give you band stop filter. So we are studying this particular thing in the next few lectures in minutest detail. So next kind of filter is all pass filter. So some of you may ask, if everything is being passed, why we need all pass filter? That's a good question. But thing is, all pass filter is required to give phase delay. So here you can find out that this is your input, this is your input, and this is your output. This is your output. So let's for change, I'm changing the color to blue. So this is your output. So between input and output, you will find out there is certain delay. So the main purpose of the all pass filter is to give delay. So if two waveforms are not matching with each other, what we can do, we can intentionally introduce delay so that perfect matching will be there. And other applications of all pass filters are there, which we will be discussing in next few classes. So I hope you get the idea fairly well. Thank you very much. And if you have any doubt, you can ask me. As already told you people, I told you people that we will be discussing in detail some numericals in the time to come. So thank you very much. Have a nice day.